Mikołaj. Okay, so hi everyone. My name is Michael. Currently I'm working at T-Mobile Poland. I'm also doing my master's at Warsaw University of Technology. So today I want to tell you about an academic project in my university, as Mikołaj said, or more precisely my contribution to that project, which was my engineer's thesis also. Okay, so let's dive in. This is the presentation plan. Firstly, I'm going to tell a bit about the background, the Wilga project. Then we'll get to the problem definition, some machine learning algorithms research, system functionalities and available tools. Then I'm going to describe the monitoring system, talk about testing and some future work. Okay, so our setting is the MIL project that I'm working, well, as it turns out, together with Mikołaj, who is present here. It is a research project, so remember that when I'm telling you about it. It's not any productional grade or commercial project. It's conducted by a team from multiple faculties of the Warsaw University of Technology. So it was created to promote energy-saving habits in retreat cottage users in Wilga retreat center that belongs to the Warsaw University of Technology. And we aim to achieve that goal by equipping the cottages with an IoT sensor network. So this is a diagram of sensors that we used to equip one of the cottages with an IoT network in Wilga. As you can see, we used some climate, motion and contact sensors and some energy meters. So I want to talk to you about monitoring. It's a pretty problematic task because of, firstly, the sheer data volume. The amount of data generated by the IoT installation is about 70 variables per 5 minutes. Well, that's a bit outdated. Right now we are gathering about 200 variables per 5 minutes. And it's scaling, it's getting bigger because we are adding new sensors, new cottages, new localizations to our project. So with scaling, that will add up, and well, using some people forces for it would be complete nonsense. So furthermore, the devices that are part of the IoT installation are heterogeneous. Different manufacturers, transmission protocols and methods, operating and power characteristics, hence the need for a monitoring system. So the task is to create a scalable and secure monitoring system that will inform the user of the current IoT network status and measured parameters, and it will detect anomalies and errors and inform the user about it in a continuous time. So let's start with the last task, as it is the most challenging one. So as you probably all suspect, and well, I talked about it a bit, the only scalable and automated solution is machine learning. So I'm sure all of you know that there are three basic machine learning techniques: supervised, unsupervised, and reinforcement learning. Of course, there are some other ones, but those three are the main three ones. So the reinforcement one isn't really used for the use case I'm having, so I won't talk about it. But the main difference between supervised and unsupervised machine learning is the need for labeled data. So for me to use a supervised machine learning in my anomaly detection would mean I would need to basically manually label every data point with the information about whether it is an anomaly or not. And also I would have to think of every possible anomaly that there could happen and introduce that data to the model. So due to the lack of resources, I decided to start with the unsupervised machine learning. So I did some research and found out that there are three main machine learning model groups used in anomaly detection in smart IoT network. Firstly, neural networks, such as CNN, we just heard about, RNN and GRU or LSTM network types. They have very high elasticity and accuracy. As you probably all know, a neural network can replace basically any function possible, so that's the perfect model. But they have pretty high resource consumption with big nets and big data sets. And I was aiming for something that could be run on a non-GPU server, so something locally, and that would run basically in real time. So that was hard to introduce. Secondly, we have clustering algorithms. An example is k-means. As the name suggests, they are good at identifying data clusters, but have pretty limited anomaly detection possibilities, especially with higher dimensional data. And lastly, we have random forests, especially the isolation forest model. It is good at operating with large data sets, especially that multi-dimensional data sets that we have, and it has pretty low resource consumption. So it's a quick summary. As I said, due to the lack of resources, lack of access to a GPU computing force, I decided to start with the isolation forest model. Okay, so anybody heard of the isolation forest model? Okay, we see some hands up, but most of you haven't heard about it, so I'm going to introduce it briefly. So it was developed in 2008 by Phaeton Aliyu from Monash University in Australia, and the principle of operation is based on decision trees. So, as you probably all know, probably all of you heard about normal random forests. So, forest consists of trees, of decision trees, and the same is with this model. Each of them operates on a randomly selected group from this input set of features. Let's take an example with just two features, like the one on the left hand of the slide, with 2 dimensions. And iteratively, when building a tree, we are creating some thresholds in the data and separating data points in the data set. And we stop that separation when we either hit when we either isolate every data point that there is in the data set, or we hit some hyperparameter-based restriction like max tree depth or something like that. And we got a tree like the one we have on the right-hand side. That's actually a tree built on our data. But the main trick here with isolation forest is the output of the model. We see we don't have any labels, so we can't say which data are anomalies, but there is a simple trick done here. We are using the path length for each data point. And the path length is the number of nodes that each data point has to go through to come to the leaf from the root node to the leaf of the tree. So let's take a quick example. Let's say we have the data point with a battery value of 20. We start at the root node. We go, let's see if that works. Okay, so we start here at the root node. We pass that test, so we go left to the child node. We have, let's say, device temperature of 8. We also pass the test and then we end up in a leaf. So that's 2 nodes that we've gone through on our way. And why is that a good way of calculating if a data point is an anomaly? Well, it's pretty simple, pretty straightforward. The easier it is to isolate a data point, the higher the chance that this is an anomaly. So the less nodes that a tree needs to isolate a data point, the more likely that data point would be an anomaly. So that's pretty simple, but remember that we need to take in consideration also all other trees in our forest. So to get the actionable model output, we need to use that formula that is on the top of the screen. We take the expected number of that path length, which is basically the mean value across all trees in a forest, and we divide it by some mean value across all data set or some subset of the data set. That depends on the configuration. And we take that as a power of 2 and invert it. So there's an implementation in the scikit-learn library of that isolation forest model. The output function is a bit tweaked. It's inverted, it's negative, and an offset value is subtracted from it. And that offset value, that's important, it's not accessible to set as a hyperparameter of the model, but it's controlled by the contamination parameter. We have a screen from the documentation here, and the contamination parameter is the amount of contamination of the data set, which is the proportion of all outliers in the data set. So when we are setting it, we're basically saying that, let's say we set it on 10%, we are saying to the model that 10% of our data are anomalies. And it will adjust that offset value in such a way that with each evaluation of the model, it will always flag 10% of the data as anomalies. And when I read it, I heard a red lamp in my head. That was not working for me because, let's take an example. I'm working on that data from an IoT installation. Let's say I have some time windows, like a month. And so I could get a month with a lot of anomalies, like, I don't know, some sensor is malfunctioning or something weird is happening in the house. Or just as well, we could get a month with no anomalies at all. And that's the ideal situation. That's what's expected to happen, what I would like to happen every time for my model not to work, basically. So basically I tweaked the function and made that offset parameter accessible by the configuration and by the API, as we will get to know later. Okay, so this is a histogram of that anomaly score, the output of the model. We set a threshold at 0 point, and we basically say that data points with an anomaly score value of higher than 0 are anomalies, and lower than 0 are inliers. Okay, so now for the far more interesting part, at least for me. You see, there is a problem with machine learning models like isolation forests, or basically most of the machine learning models. The interpretability. As you probably all heard about the black box model. Well, all of the machine learning models, well, most of them are like a black box. Some parameters coming in, something coming out. We have no way of saying what was the impact of each feature coming in on the model output. And that's really important to me because, let's say I have a data point that's flagged as an anomaly. I would like to know what was the influence on the model and what caused the model to select that data point as an anomaly. So there are some solutions for it, for interpreting these black box models, and one of them is called SHAP. It was developed in 2017 by Scott and M. Landberg from the University of Washington, and thanks to it we are able to determine how much each feature impacted the model output. So, Shapley means Shapley additive explanations. It's based on the contribution to the theory of games by Lloyd S. Shapley from 1953. So that's an old article. So Mr. Shapley created an algorithm to calculate the impact that each player has on the game output. And it's calculated by performing the game multiple times with different set of input players. And basically the same thing we can do with machine learning models, but the players are the feature values and the game is the machine learning model computations. And by performing the machine learning model computations multiple times, we are able to say how much each feature value impacted the model output by using a formula that is at the top of the screen. And it's also with the SHAP library comes a lot of useful visualizations. Like the one on the left, we can see one data point with all of its features and the sharp values associated to that, to those features. Like the battery value, we can see how it was 34%, and that value had a negative output on the model, quite a big negative output by minus 2.38 nodes. That is the raw output of the model, so that it's measured not in that anomaly score, but in those that expected path length we just talked about. So we can see that the mean output of the model, the mean number of nodes that each data point has to go through, was 11.4 nodes, and all of that features combined, Shapley is additive, so we can add those features together, gave us the output, the actual output of the model, which is 6 nodes. And that feature is an anomaly because of that. And we can get also some pretty great insights to the data set. For example, the B-spline plot. On the right, we can see what generally influenced the model and how. For example, that battery value, a lot of battery values were high, and they had pretty positive impact on the model output, and the lower battery values, which were lower numbers, also had a negative impact on the model output. Okay, that was a lot of theory. Let's back up a bit and get to the technical side of our use case. So here you can see a technical diagram of the MIL project. In the edge network, we have Zigbee and Wi-Fi sensors connected via a WireGuard, a VPN, to our main server, which holds the MQTT broker that handles all of the data flow. And from that broker, we have to take the data, monitor it, analyze it, and inform the user about our findings. Okay, so these are the desired functionalities of a monitoring system. Firstly, it has to perform the data acquisition, it has to store the data, it has to perform the data analysis, including that machine learning models that we just talked about. It has to visualize the data and inform the user about its findings, any important events. Okay, now let's get to the research. I did some research and found out some existing tools that can be used on to some of those use cases, some of those functionalities. Those include InfluxDB, Grafana, Zabbix, Prometheus, and ELK Stack. Of course, there are a lot more applications that I could use, but these are the most, well, for me, they seem the most fit to the task. Well, none of them checks all the boxes except of the ELK stack. But as I said before, you need to remember this is an university project, a research project, so we did not have access to some funding to buy the pretty costly ELK subscription. And also ELK is pretty heavy. It needs, basically with all of its features, needs a cloud to perform normally. So that was not possible on a local server. So we decided to go with a combination of InfluxDB and Grafana. And use the InfluxDB as a database and an acquisition tool, and Grafana as the visualization and alarming tool. You may notice that none of these tools have the analysis and machine learning capabilities, so I had to make them on my own. Okay, so this is what I came up with, the monitoring system diagram. It consists of 5 modules, so let's take them step by step. Firstly, the data acquisition and the database. As I said, the MQTT brokers handles data flow. Tags are kept in the topic structure, that way it's easier to perform the acquisition. We are also using the QoS equal 1 to ensure that all of the data comes from the edge network to our main server. And we are using a feature called durable connection. It makes the data acquisition tool able to become offline for some short periods of time and stores that data that was intended for that acquisition tool, and then when it comes back online, that data is sent to the acquisition tool. So as a data acquisition tool, we are using Telegraf. It is a standalone automatic tool by InfluxDB. It is optimized for large data volumes, and well, basically it's one of the tools that I would recommend with very much, because it's working great when I got through the configuration, and well, it's a bit less well documented as I would like it to be. But when you get through that configuration, it's working really great. It's written in Go, so it works really smoothly. I would totally recommend that. And Telegraf pushes the data to InfluxDB, which is a non-relational time series database optimized for large volumes of data. And of course, we use tags as a way to label our data. So we have now our data in the database. We now need to perform that machine learning analysis. So for that, I decided to go with a microservice kind of architecture. I used Python as a programming language. Of course, we are at the Python Summit, why anything else? And with Docker runtime and Zipper API by Flask to handle configuration. So this is a complete module logic. The whole well, microservice works as a moving time window. Each time interval, it works on data collected from some time window. And of course, you can use that API to handle configuration and change it and do whatever you like. This is the complete data flow. Firstly, we retrieve data from InfluxDB. Then we do some pre-processing. Then we perform the isolation forest computations, from which we get the anomaly score value, which is the output of the model. The anomaly label, which is the information about whether that data point is an anomaly or not. And then we perform that SHAP algorithm computations, from which we get only one value, which is the anomaly reason. You see, SHAP gives us a lot of insights to our machine learning model, but most of it isn't really useful to an end user. So I decided to quantify that information and pretty much make this a simple string, so the user could read it and decide, and that could tell him about the most influential feature in that data point. So basically what it is a string containing information, what was the most important feature, how big was the impact, and in what direction was that the impact. For example, we can have let's say negative low battery value, and that's saying that the battery value was unusually low. It had a negative impact on the model output. Simple as that. And of course, we upload that results into InfluxDB. Okay, so now let's get into Grafana, which handles the data visualization module as well as the alarm module. So the alarm module is based on the Grafana Alert Manager. I have configured some alerts like anomaly detected, device inactivity, whole system inactivity, low battery level for devices, high temperature in the IoT cabinet. That is really a reason of a problem we are having with those high temperatures in the box when we store our whole logic in the edge network. So we installed a sensor, made an alarm, and now we are notified each time that something bad happens with it. And also wasted energy. I will get into that later. It's project logic based. And each alarm is visualized in the data visualization module in Grafana, and also is being sent as emails like the one we can see here, with labels, with description, and with templatable summary. That's a great way to use it, because we are able, well, I was able to template it in that way that each user which is, well, hasn't got the whole information about the system can, by that little summary, can say what was wrong and why the model acted the way it did. So, for example, we have anomaly detected with negative low power bathroom having an unusual value of minus 1K. Okay, so let's get to the last module, the data visualization module. It was developed to display the current system status and errors, and it should display that information in two visualization ways. Firstly, the overview mode, which is the, well, it was an idea to enable the user to get the most important information that he needs right now, so the system status and if there are any errors. Only that, no other distractions, and with a simple look at the screen, he should be able to tell if everything is okay with the project and if there are any errors. And also the detailed one, which is the opposite of the overview mode, for the user to be able to browse through every data point, to debug the whole model, and well, basically get into the data. Okay, so when we log into Grafana, this is what we see. Is the overview mode, the main page. We can see a map of houses that have IoT network in them. Each house has an icon that can be green or red. Of course, green states that everything is okay with the house, and red that there are some alerts originating from that house. And on the right-hand side, we can see all of the alerts that are firing right now in the system. We can, of course, browse them, see the summaries, labels, click into them, get into the data. But basically, that was the idea for the user to see the screen. If everything is green and the right-hand side is blank, then everything is okay. If not, as we can see here, something is wrong. And if we click on one of the houses, we can go to the health dashboard. We can see more detailed information here, like all of the alarms in the system, like inactivity of each data point in the system, like the service temperature I was talking about in the IoT cabinet, or the device's battery. And we can also see the most anomalous telemetry in the whole system. So that was the idea. Let's skip to the anomalies view. We can see here the anomaly chart, and we can see the anomaly reason value, which is a way to debug the model. We can see for each data point what was the model input, what was the model output, and we'll decide if some hyperparameters needs tweaking or something like that. And we can also see the contamination of the data set, the amount of anomalies in a selected time window. Okay, so let's go back to our main page and click on the overview mode. It's the dashboard containing the most important information in the house and the localization. We've seen it all pretty much. Firing alerts, times latest activity, the presence of people in the house, some energy cumulative sum, and the energy waste. I will talk about that in a short moment. Now the energy dashboard. We can browse through each appliance that is generating energy usage. We can see how much of the whole energy usage each appliance used. And we can get into the energy waste, which is at the bottom of it. Energy waste is it's something that we decided to do because of the whole project. The project was intended to promote those energy-saving habits. So we have to have a way of scoring the users with energy usage. So using the data that we had, we created some basic logic, like, for example, let's say we have a heater in the house, that there are 2 heaters in the retreat cottages, and the energy is considered wasted when it's used by a heater, and at the time that the heater is running and the window is open in the house, in the same room that the heater is in, or the temperature in that room exceeds some set threshold, like 23 degrees or something like that. So that is considered wasted. And also the same thing with TV. if the TV is on and no one is in the room that the TV is located in, then the energy used by the TV is wasted. And in that way we can like score the users with the energy usage and say how much of the energy they are using correctly and how much not. We are planning on adding another factors like heating, water heating, or other things. We can see here the occupants dashboard, more information about that energy waste, the presence of users, the location of the users, and the estimate number of occupants in the building. And if we really want to get into the data, we can see the raw dashboard, the raw values per each room as a way it was intended. Okay, so that's all from the view. Let's go into the testing. So the most important part, the most important one, was the field test. The monitoring system is working on the Wilga mill project for a year now and has successfully identified many anomalies and errors, such as inactive sensors or user fault. A great example is that one time we got an email from the monitoring system saying that it's 70 degrees in the bathroom, I think it was, 70 degrees Celsius, so that's a big number. We were worried for a time that it was a fire in the house, so we called the retreat center. And basically, it turns out someone had left the heater on during the night, and it's a really small bathroom, so it heated to those 70 degrees. That's amazing. That's a beast, that heater, yeah. So that's that. And also, I made some testing software that was designed to impersonate the sensor. It simulated some wrong reading, like here the integer overflow, or some malfunction of the sensor, or influenced by that situation, a natural disaster like a fire. And everything worked. Well, the model is good at identifying those anomalies. The only real downside of it was that we've got a lot of false positives. So the model is usually, I tried tweaking the hyperparameters, but well, a lot of the times it's saying that something is an anomaly and it doesn't look like it. So, well, that's a feature of the unsupervised machine learning, that you don't have a way of saying to the model which is wrong and which is okay. So that is the field to improve in the future. So in the conclusion, we have a model that is, well, a system, monitoring system that is fully data-based, that is stable, have identified successfully many alerts, and has a lot of false positives. So for the future, firstly, I want to make, my dream is to make a tool, GUI for machine learning model control with a whole kind of a machine learning ops backend that the user could schedule machine learning jobs, pause them, resume them, maybe provide some input to the model, like say that, well, it's a correctly identified anomaly, or saying that it's complete nonsense, try again. We may also consider changing architecture to cloud-based, for example, Kubernetes or some cloud provider like Azure or AWS. Of course, further isolation forest improvements, like using some multiple different time windows or adjusted pre-processing algorithms. We can also use some advanced other isolation forest modifications like the X forest and extended isolation forest, and some further feature engineering. And of course, the most important for last is comparing other machine learning models, the thing that I'm doing right now. Firstly, I want to get into the autoencoders. That's a handy trick of letting the model get to know with the data that we are having, and then processing out on the data, and if it detects something other than the usual pattern, we flag this an anomaly, basically. And those include RNN, LSTM, and GRU type of networks. Also the autoregression based models, like a simple autoregression or the profit model by Facebook. I already tried it a bit and it looks promising, so probably that'll be a good idea. And if I get the time, we may try also some classification models. Maybe I force myself to label that data and maybe make some actual data set that can be used for classification. Okay, so that's all for today. Thank you very much, and please rate the presentation.
Thank you, Michał, very much for the presentation. I must say that your anomaly detection system works pretty well, because during the presentation I got 2 emails about anomalies. So I assure you that it works well. I think we have time for just one question. So if you have a question, then do not hesitate. Okay.
I have a question about latency in this system. What latency have you measured from the anomaly appearance till detection till sending an alert?
Okay, so as I said, it's working like a moving time window, and it depends on the configuration, because right now it's configured to perform the computation about once per 5 minutes, I think. That's the current idea, and basically that's that 5 minutes when it lands in the database, and then alert evaluates it. But we may, if we have the need, we didn't have the need to perform that, well, to get the data faster than, well, at least 10 minutes or so. But if I would like, I could increase that, well, decrease that latency to, I think the machine learning computations take about 10-11 seconds, so that's probably will be the latency plus evaluating that alert. So probably about 30 seconds, I think, mostly, yeah.